All right, off we go. So today we're going to continue on with our look at these key ingredients for inferential statistics. This time we're going to start moving towards more about the normal curve and its importance and just some features of it and why it pops up over and over and over again. And this again is in service of getting to the final goal, the really cool stuff that we can do with statistics, the looking at actual data and making actual decisions about does a treatment work or does it not work? Are there a difference between two groups or is there no difference? But we're still laying down that foundation, still working on our fundamental pieces. And again, one of the end goals of this is to get those pieces, those parts of it, so clear in our minds that when we put them all together, the only mental effort is going to be in the actual putting it together and not in the doing of the individual parts. So the more automatic you are on z-scores, the more automatic you are on reading frequency distributions, the more automatic you are on working with the normal distribution, the easier and more straightforward it's going to be once we finally put all those pieces together. And again, we'll keep hammering home this example. This is what it's all about. So once again, if you graduate from IUSB and you become an educational psychologist, and let's say that you are assigned a classroom of 14 autistic children on the spectrum, and because of your psychology training, you decide that a more interactive method of teaching would be appropriate for these particular students. It would increase their learning outcomes. What you can do is you can measure their learning before that interaction, measure their learning after that interaction, and if their learning increases, if there's a positive change, without inferential statistics, all you can say is that your treatment worked for those 14 students. And that is it. That's where the story ends. So as a psychologist, you would be able to invest, let's say an entire semester, 3-4 months of time, you'd be able to invest 4 months of time to help 14 people. And that's good, but it's not great. Great would be to be able to help 14 million people. And that's what inferential statistics allows you to do. It allows you to look at those 14 and then say, is this a real difference? Did this treatment make a real effect? That is, would this treatment work for the population of autistic children? And as soon as you can figure that out, then you can help not just your 14, but every single autistic child in the world who is either currently around or will be born in the future. You're able to help the population. So always keep that in mind. It's about going from a sample to being able to say something true about an entire population. All right, and one of the ways that we're going to get to that and be able to do that is through the normal curve. So this will just be a really brief recap. The normal curve is something that occurs in our universe, in nature, in humans, over and over and over again. So we saw that it is the result when a number of different factors come together for a certain outcome. And in an individual human, there are very few things that we do that are the result of one factor. Most of the things, most of our behaviors, most of our characteristics are due to multiple factors coming together. So even in individuals, most of our characteristics fall on this normal distribution. But we're going to see that it goes even farther than that. And it also applies to the scores of samples. They also fall under this normal distribution. And that's what really opens up psychology to be able to help everybody. That's what makes statistics even possible, inferential statistics even possible as a technique. So that's what we're going to be focusing on today. So just a really brief recap of z-scores and the normal curve table, how to read it, how to answer questions with the table, and then we're going to dedicate some time. It's been a while since we've had in-class practice. We're going to dedicate some time to actually doing work on an Excel sheet to make sure that we know how to do this, know how to read the table, know how to go from a score to a percentage, from a percentage back to a score. And then we're going to wrap it up with a look at samples and populations, be very clear about the difference between samples and populations and what that means. We're going to take a look at the distribution of sample means, and then wrap it all up, hopefully if we've got time, with a look at the central limit theorem, which is the magical thing that allows inferential statistics to operate. All right, so if you recall, last time we went over this, when you're dealing with z-scores in the normal curve table, two of the things that you will use this table for often is going from a raw score to figuring out a percentage, or going from a percentage to figuring out a raw score. So as we saw last time, there is a 5-point or 5-step procedure for doing this. In your textbook, it's only got the 4 steps because I added in step number 2, draw your normal curve, which I highly recommend. And we saw that if you are asked a question, given a certain distribution, so for example, for a distribution with a mean of 500 and a standard deviation of 100, what percentile rank are you in if you scored a 333? So this is when you're starting with a raw score, you got 333, and you're being asked for a percentage. And we saw that when we go through those 5 steps, we ended up with a percentage of 4.75. You're in the 4.75th percentile with that particular score. The other thing that we looked at was when you're starting with a percentage. Starting with a percentage still has 6 steps. So if you want to know what score do you need to achieve to be in the top 1%, in that case, you're starting with a percentage, you're being given that 1%, and you're asked for what score is associated with that 1% in the top of the distribution. And once again, it was a 5-part or 5-step procedure. In your book, once more, 4 steps. I added in the extra one, draw your normal curve. Be sure to do that. And we saw that in this case, you end up with a z-score, and then that will give you your raw score, which for this one was 733. So if you score 733, that will put you in the top 1% of that distribution. All right, so what we're going to do now is we're going to dedicate some time in class to the practice sheet that I put together. So this is in your Canvas files, in your Excel sheets. It's week 6, class 2, practice chapter 4, probabilities. And what I'd like you to do is work through this worksheet. There are some basic questions. The first ones are basic questions about reading the table and figuring out probabilities. So that's the first 3. The last 2 are about going from a percentage to a actual score, or from a score to a percentage. So we are going to dedicate about, let's go maybe 15, 20 minutes to this, and we'll make sure that everybody is on the same page, everybody's able to do this. Incidentally, you may want to save question 3. Question 3 is a true test. It's a little bit further than I would expect people to be at this point, but if you can get question number 3, then you are definitely really in a solid position to continue on and basically destroy the rest of the course. All right, so practice time right now. Call me over if you're struggling, if you're having difficulties, and we'll make sure everybody is on the right path. Oh, and I did mean to mention this before we got to practice time, so just real quick. So don't forget, for the innovations and suggestions for this week, that survey is now open, so look for the link in the announcements to contribute any of the ideas that you might have for this week. If one of your suggestions didn't get picked for the top 5 this week, you can actually resubmit that suggestion. Maybe it'll make it into this week's top 5. And also look for the tweet that I sent out earlier this week. A lot of students have been voting on their favorite of the 5 suggestions, so just make sure that you do that as well. And I will be figuring out who the winner is on Monday. So let's we'll take a little bit of a break. So we'll continue with more practice time, but I do want to just real quick show question number 3. So if you are able to do question number 3, that is a really kind of good indication that you are more than exactly where you need to be for this level. So in question number 3, what this one is practicing is it's practicing your ability to use the unit normal distribution table, use that appendix in ways that it's not necessarily set up to be used, right? So we've already encountered this idea that it's not set up to immediately give you all the information that you need, because in the first 2 questions, if you were asked for, here's the z-score of 0.43, how much of the distribution is below this z-score, that answer wasn't anywhere on the table. We had to use a little bit of logic and math to figure out that, if we have a z-score, if that's 0 right there and that's 0.43, and we want what's below, that we have to take that portion from the table, and then to that we're going to have to add the remaining portion, which is the 50%. So that's one of the reasons why I highly recommend, when you're doing things with the unit normal distribution table and distributions just in general, draw them out. Just a real quick sketch on a piece of paper. It doesn't have to be to scale. All we're really looking for is the areas that we're trying to figure out which areas do we need. So we've already seen this idea where you have to piece together parts of the table in order to answer a particular question. So let's take a look at question A in example 3. And once again, you want to draw out your distribution. And this time, we're asking for kind of between parts, right? So we have 0.45. So let's call this 0.45. And then we have 1.45. So let's call this right here 1.45. And we want to know the area between those 2 z-scores. So we have this area right here. That's the area, that's the squeaky area that we want. And that's not going to be anywhere in the table. So we need to try to figure out how can we piece together parts of the table in order to get that particular answer. So in this case, one of the ways to do this, and there's usually multiple ways, but one of the ways to do this is to break this up into 2 parts. So if we have this distribution, and we have 0.45 right there, in the table, we will have that section of it, right? So in the table, it will tell us what percentage is in the tail, right? So we can look that number up. Also, in that same kind of idea, if we take a look at 1.45, which is right there, that'll also have this area listed in the table. It'll also tell us how much is in the tail. But notice that what we have here is we have the 2 parts that we're going to need. Because if we're interested in this red area right there, the area between 0.45 and 1.45, what we're looking for is we're looking for the area in the tail above 0.45 without the part that is above 1.45, right? We want what's above 0.45 without what's above 1.45. So if we look at the tail, what's above 0.45, and we look at the tail, what's above 1.45, we can then take this number and subtract from it this number. And the area that's left over was the area that we wanted. So in question number 3, you have to play around with these kind of looking for these sections and figuring out how can we piece together that part of the normal distribution curve by pulling from either the tail information that we have in the table or between the mean and the z-score information that we have in the table. So that's how you would do the first one there, but that's not necessarily how you're going to do the second one. The second one, you're going from a negative to a positive one. There's another way to do that. So if you finished questions 1, 2, 4, and 5, that would be a good, challenge for you to do. And if you can get those, that is beyond where we need to be at this point. So it'll be a really good indication that you are super set for inferential statistics and hypothesis testing that is coming soon. At this point, what I would like to do, let's take a break from the practice, and we'll just mention a few things and kind of introduce one new idea that we'll end today's class with. All right, here we go. Okay, so the first thing that I want to point out is there was a typo. Some of you caught this morning. Your homework assignment, your next one, is not due in June. It is due on, what do I got there? It's going to be due on Wednesday, October 9th. All right, so we got time on this one. This is the more advanced part of that normal distribution homework. So make sure you work on that. Try the rest of the practice Excel pages, and just make sure that you're very comfortable working with that normal distribution table, because we're going to be going to a table, either that table or tables like that table, once we get into doing our inferential statistics. All right, as always, remember your MyStatLab study points. I'll be, again, updating your pretest points with your MyStatLab study points. And that's especially important going forward because, again, doing pretests, even if you're struggling, has been shown to give big payoffs in terms of improving the learning outcomes. But again, I want to insulate you from any harm that you might get towards your GPA for taking advantage of this. So that's where the MyStatLab study plan comes in. You can always earn those points back so it doesn't impact your grade. All right, so what we're going to wrap up today is our sort of intro to a very important idea, a very crucial aspect of statistics, really what makes psychology possible, right? It's what makes us able to help the millions instead of just the 14 students in our particular experiment. So it all boils down to samples and populations. So this is where the book now flips a switch on you and goes from talking about all the things you can do with populations to having to deal with a sample. This is where the book finally catches up to where we were, where we differentiated samples and populations from the get-go. So you only ever have access to a sample. Unless you're the Census Bureau, you never have access to population data. And even they don't really have access to population data. A population is everyone, everybody. So we only ever have access to samples, but that's fine because you can use those samples to estimate those population parameters. So if I was interested in the average age of an IUSB student, I would not have to go and interview every single IUSB student. I would just take a sample. I would ask maybe 100 and ask them for their average age to see what that estimate for the population age might be. Now, when it comes to most psychology questions, and most of what psychology does, we want to say something about a population. And in most cases, we have no idea about the parameters of that population. And this is especially true when you go into, for example, clinical practice or in experimental psychology when you're dealing with new populations. So we do know what the population distribution looks like for IQ scores, right? It's got a mean of 100, it's got a standard deviation of 15. But what about IQ scores amongst single children? We don't necessarily know that. What about IQ scores among people that spend more than 12 hours a week on social media? We don't know what that is either. What about an IQ score for any population that we might be interested in? Typically, we have no idea. So we're typically in this situation where we don't know what the mean is, we don't know what the standard deviation is. So what do? Well, we start taking a sample from that population. If you're interested in the effects of social media on intelligence, you might take a sample of high social media users and give them an IQ test, see what their IQ scores are. So we start taking a sample, and let's say that we take those 5 individuals. So these are the 5 individuals that we use in our sample, and from those individuals, we can calculate a sample distribution, and we can actually measure their scores. So now we have a known mean, and now we have a known standard deviation. We can actually measure these, figure it out. This is data that we have. However, in this case, notice that our mean for our sample lines up with the center of this population distribution. The mean for our sample lines up with the population mean. So in this case, our sample is a good estimator for our population mean. Our sample mean is close. Actually, in this case, it's exactly the same as a population mean. That's great. We don't know if that's the situation because our sample could have been those 5 individuals, but our sample also could have been these 5 individuals. So they are still part of the population. They are still eligible to be part of our sample. We've randomly chosen them from the population. Remember, we don't know what the population looks like. So we have no idea if these 5 individuals are actually extreme members of the population. So in this case, when we calculate our sample, we will end up with a mean, we'll end up with a standard deviation, and unknown to us, we have no idea, we've vastly underestimated, in this case, the IQ of the population. So we got 5 people with low scores, but we don't know that they're low, we don't know they're from the lower extreme of the population. So in this case, our estimate is underestimating the actual population score. And likewise, we might have ended up with these 5 individuals over here. And in this case, once again, we can calculate our sample. We have our mean, we have our standard deviation, but now we've vastly overestimated what the population mean is. And again, we have no idea that we did this because we don't know what the population actually looks like. That's why we're taking that sample. So that is the challenge that we're going to be addressing here. So different samples from any population are always going to end up with different sample means. So if you take 5 people out of a population, you test them on some measure, it's going to be different for the next 5 people that you take out. And it's going to be different for the next 5 people that you take out. So most of the times, your sample mean is not going to equal your population mean. Sometimes it's going to be very close, sometimes it's going to be far away, but most of the times it's not going to equal it, and that's called sampling error. That is called, that's the difference between what the actual true value is and what your measured sample estimates it to be. So this sampling error and the fact that these different samples will have different means leads to sampling error, but we're not helpless in this situation because we can take advantage of the fact that different sample means will have different probabilities of occurring. Not every sample from a population is equally likely to occur. So we'll stick with the IQ example. Let's say that you and your friend have been invited to the IQ Olympics, right? Let's say that they have an IQ Olympics, and you get your invitation in the mail, and you're going to be forming a team of 6 individuals, right? You're one of the 6 individuals, and your friend is on another team. They're going to have 6 individuals, and you're going to be forming a team of 6 that are going to go compete as a team in this IQ Olympics. And you're sitting there and you're going, ooh, I wonder who my team is going to be. I wonder what my random sample from the population is going to be. So you show up on the day of the Olympics, and they say, we'd like to introduce you to the rest of your team. And there's your team right there. And your team consists of pretty regular people, right? So we have an individual back here. She graduated university. We have this guy over here. Maybe he's a high school. He finished high school, but no university. We might have this individual over here. She's in grad school. We might have this individual over here. Maybe he didn't even finish high school. Basically, we have people who are very typical, very, I don't want to say normal, but very much from the middle of the distribution. Nobody's super extreme on your team. If you were introduced to that team, you might say to yourself, well, you know, believable, right? I didn't get super lucky, I didn't get super unlucky. That's a very believable team. That idea, it's a believable team, means that a sample like this is highly likely to come out of the population. If you just start pulling people at random from the population, you're going to get some people who are above average intelligence, you're going to get some people that are below average intelligence, but most of them are going to be pretty close to the middle of the distribution, like these 5 individuals here. So that's your team, and you would intuitively feel very likely that that would occur. All right, so that one has a very high probability. That sample and their mean intelligence seems to have a very high probability. So you talk to your friend, you meet up afterwards and you say, oh yeah, I just got introduced to my team for the IQ Olympics, and they seem like a pretty likely bunch. What about your team for the IQ Olympics? Who did you get on your team? Because remember, we're randomly picking people from the population of individuals on Earth. And your friend tells you, oh my gosh, I couldn't believe it. I walked in there and my first teammate, Bill Gates. Oh my goodness, right? So in terms of IQ, all right, if we got IQ scores over here, in terms of IQ, we got somebody, Bill Gates, from probably right around there. All right, so you think to yourself, oh wow, that was lucky. That was a lucky first draw, random draw for your team. Okay, so who's your next member? Who's the next member on your team? And he's like, wow, you wouldn't believe it. Team member number 2, Neil deGrasse Tyson. What are the odds? And you start to say, pretty slim, right? Because Neil deGrasse Tyson, also an extreme example. And you're like, all right, well, what's your next team member? My goodness, Bill Nye the Science Guy. And at this point, it starts to boggle the imagination how unlikely it is that out of 7 billion people on this earth, 3 picks are going to be Bill Gates, Neil deGrasse Tyson. I don't know which one is above which. We'll just start putting circles on top of circles. Neil deGrasse Tyson and Bill Nye the Science Guy. And then if you continue going, well, who's your 4th member? And they're like, oh my gosh, you wouldn't believe it. Marilyn von Savant, the highest recorded IQ ever, right? So she's probably over there. And if you're like, oh my goodness, what are the odds? They're astronomical. Who's your last person? And they go, yeah, Ruth Lawrence. And if you don't know Ruth Lawrence, she's a mathematician who got her bachelor's degree from Oxford at the age of 13. All right, so I don't know where she is. We'll put her somewhere here in the middle. Okay, so that's their team. Randomly chosen from the population. No shenanigans. Randomly chosen team from the population. So you're sitting here with this team. Randomly chosen from the population. Your friend is sitting there with this team. Randomly chosen from the population. And we know and we feel that this is way less likely to occur than this. So this team is way more unlikely to ever be put together randomly than this team over here. And that's what we can take advantage of when we're dealing with samples. We can figure out how unlikely is a sample like this to have occurred. We can actually get numbers on how unlikely would this sample be. So rather than just saying, oh, it is extremely unlikely that you would be able to put together a team like this, we're going to see how eventually we can say this is a 1 in 48 trillion chance. We can assign a probability to this, and that's going to be how we're going to end up doing our hypothesis tests. All right, so again, that's the challenge. We don't know where our sample came from in the population. So how do we get over this and use these samples to estimate populations? How do we specifically get the probability of a sample coming from a population? So what is the probability of getting any particular sample? And we're talking about probabilities, and hopefully by now it's in your mind, statistics, probability equals a proportion. So it's a proportion of what? It's a proportion of a distribution. So the final thing is to answer what distribution. So we're going to go over this a few times. I want to introduce it today so it can sink in over the weekend, because this is one of those items in statistics where your ability to deal with distributions is really going to pay off, because the distribution of sample means is literally like a distribution of distributions. So we're getting at like inception level, type thinking here. So the clearer you are on distributions and sample means, the easier this is going to be. So a distribution of sample means, that's the distribution that we're going to be using to say that this is highly unlikely to ever occur. So your distribution of sample means, it is a collection of every possible sample mean from a particular population of a certain size. So it is literally the distribution that you would create if you took, get rid of this thing here, and the numbers get so huge that it kind of boggles the mind. But let's just roll with it a little bit right here. So let's say that we were looking at these IQ teams. And we had certain samples, and then we measured their average IQ. So we take out sample number 1, 6 individuals, right? Randomly from the population. Give them an IQ test, measure their average IQ. Let's say that they score 105. What we do is then we send that sample back, and we pull in another sample of 6. That's sample number 2. We measure their IQ. Maybe we get a 97. Throw them back in. Take in another sample of 6 individuals. That's sample 3. Measure their IQ. Maybe that'll be 115. Throw them back. Take in another sample. Measure their IQ. Take in another sample. Measure their IQ. Take in every possible sample of 6 individuals on this planet. So eventually we'll be at sample 1,487,267,487, right? We have that sample. Measure their IQ. Turns out that one is 101. And we keep going until we have all of them. Once we have all of them, we have all these sample means. We make a distribution of these sample means. We treat them like any raw scores, and we make a distribution of these sample means, and we end up with our distribution of sample means. So the name is on the tin there, but importantly, it's a distribution of means that come from a sample distribution. So let's, we'll introduce this idea right now, just to kind of show you where we're going with this, and then we'll wrap it up for today, so we'll let this sink in over the weekend. All right, so this is if we're dealing with a population. Let's simplify it a little bit. Let's take a look at the population of dice rolls. So the population of dice rolls, rolling a single dice, the mean, if you were to go and take a look at every single fair dice that has ever been rolled, and take a look at the distribution of every single fair dice roll that has ever occurred, and calculated the mean, you'll find that the mean is 3.5. Because a dice roll can go anywhere from 1 to 6. The middle of that is 3.5. So right there is the mean of the population, right? The balance point of the population. Let's say that you're sampling this population by taking a look at single dice rolls. So much like what we did here, we start taking every single possible sample of dice rolls. And there's only 6 of them, right? There's only 6 possible dice rolls, and their means would be 1, 2, 3, 4, 5, and 6, right? So if you roll 1 dice, you roll a 1, the mean of that is 1. You roll another dice, you roll a 5, the mean of that roll is 5. You roll it again, you roll a 6, the mean of that roll is 6. So if you take a look at the mean of all the sample means, and there's your inception thing, if you take a look at the mean for all the sample means, you'll find that your mean is once again 3.5. That's very important because that, you'll notice, matches up with our population mean. That's going to come back later. If you draw this distribution out, right, if you graph this distribution, you'll end up with a sampling distribution or distribution of sample means, and in this case, and this case only, your distribution of sample means looks like your population distribution. And that is only for a sample size of 1. That's the only time it occurs. So let's get off of this and take a look at what happens when you roll 2 dice. So we're going to do every single sample, every single possible combination of 2 dice. So if you roll 2 5s and you figure out the mean, 5 plus 5 is 10 divided by 2 gives you an average, a mean, sample mean of 5. You roll 2 dice again, you get a 7. Average of that is 3.5. You roll 2 dice again, you get snake eyes. The mean of that roll is 1. You keep rolling dice after dice after dice after dice, 2 dice after 2 dice after 2 dice, until you get all 36 possible means, add up and find the average of all of those sample means, and lo and behold, the answer is going to be 3.5. So notice, once again, 3.5, 3.5. That's the pattern that is going to become very important. Importantly though, now if you were to graph that distribution of sample means, how many times does each of these sample means occur? That's the answer you get. So no longer does it look like the population. Right now, some of the means, like 3.5, are much more likely. Other means, other sample means like 6, are a lot less likely. So we continue doing this. Now we're going to increase our sample size to 3 rolls. So now we're rolling 3 dice. Once we roll the dice, we add up the scores, we divide by 3. So this sample here would have a mean of 5. If we roll all 3 dice and the total is 12, that sample has a mean of 4. If we roll all 3 dice and the total is 9, that sample has a mean of 3. And once again, we record the means for all, what is this, 36, 196 rolls. All 196 rolls, I think I did that right. All 196 samples, we record the means of all of those samples. If we did that, and we found the average of all of those sample means, that's what the average of all the sample means is going to be. Once again, exactly what the population mean is. And once again, this distribution of sample means changes to look more like that. And we keep playing this game. We do 4 dice rolls. Take a look at every single possible sample of 4 dice, find the mean for each of those samples, then we find the mean of all the sample means. Turns out that mean, we've seen this again before, 3.5, but now the distribution of sample means looks like that. And we'll finish the analysis. I got one last little space there. So we'll finish the analysis. Here we go. If we do that for 5 dice rolls, no surprise, the mean of all the sample means is going to be 3.5. And we end up with a distribution of sample means that looks like that. So that distribution of sample means, or that sampling distribution, that is what we're going to use to tell us how unlikely a certain sample is. That's what we're going to use to tell us that getting Bill Nye and Marilyn Von Savant and Neil deGrasse Tyson on your team is super, super rare. Look at the frequency with which it happens, barely at all. But getting that average team is much less rare. That's how we know what's the probability of getting any particular single sample. And if you take a look at the shape of this, it is not a coincidence that this looks very much like a normal distribution. And that is where statistics and psychology merge and are able to do things. Because there's a reason why psychologists do studies with samples. There's a reason why we take a sample of 20 individuals. We take a sample of 150 students. We take a sample of 30 people who are suffering from depression. We take samples because as soon as we take samples, we know that the mean of those samples is going to fall on a normal distribution. So that's why we're putting in all the work right now and dealing with that table, because that table is going to occur over and over and over again when we take a look at how to analyze experimental data. All right, so let me just... So we will go into more detail, more background on that next time, but that is where I want to kind of end up for today. So we got about 4 minutes left. If anybody has any final questions on anything, feel free to let me know. Give that Excel sheet a try if you haven't already completed it, and make sure that you are very comfortable using that table, knowing which column to look in, knowing what to do with it, because that's the table we're going to use for the rest of the semester until we switch gears and use a very similar table in exactly the same way. So the tables are going to change, but the basic idea of reading the tables is going to stay the same. So make sure that you're putting in that effort. And if you haven't already, make sure you're voting on those innovations and suggestions. Feel free to contribute to this week's survey. And other than that, we're done for today.